Welcome back. In the last class, we discussed about spin echo and attached proton test to discuss and identify different carbons based on the number of protons attached to it. That was called attached proton test. Afterwards, I wanted to introduce polarization transfer. We saw what happens to the polarization transfer and two homonuclear weakly coupled spins were considered. We saturated one of the transition, we saw change in the intensity of the other coupled spin. We also inverted one of the transitions of the coupled spin, we saw change in the intensity of the other coupled spin. Now we extended the logic to what happens in heteronuclear case, because in the case of heteronuclear, gyromagnetic ratio, and I'm now taking the example of proton and carbon gyromagnetic ratio is 4 times smaller than that of proton. There again we selectively saturated one of the signals, selective polarization transfer we did, saturation transfer we did for one of them. When we did the selective polarization transfer by saturating one of them, we observed this. We had taken for the purpose of understanding 10 spins here, 2, 8 and 0, 0, so that the intensity ratio for 2 protons signals and 2 carbon signals in the doublet pattern remains 2:2:8:8, because as you know, this one is always much smaller compared to proton, 4 times smaller. That's why that was the population ratio chosen. We also observe what happens if I saturate one of them. We saturated this peak, this proton peak, because we are transferring signal from magnetization from proton to carbon. So we'll saturate proton and see what happens on carbon. We saturated this signal, especially this peak, 1 to 2. See, it was when we saturate the populations which were more here, about 10 and 2 here, now I made it equal 6, 6. That's all. We saturated only one proton peak. See the effect now. Calculate the intensity ratio. This one in this case, I saturated. This is intensity 0. Whereas in this case, the signal 8 minus 0 remains same. It is not affected at all. What about the carbon signal? Look at it. This is 6 and 10. The difference is minus 2. We are seeing 2 here. What about here? 6 minus 0, intensity is 6. So we saw there is 3-fold intensity increase for one of the carbon-13 signal by saturating a proton signal. We saturated a proton transition and enhancement in both the carbon doublets we saw. Of course, one is negative in sign. I didn't see the enhancement is up till now. We have not seen. We'll see later. And we saw for one of the signal, one of the component of the doublet, enhancement of the signal was seen. So selective inversion of a proton transition, let us see what happens in heteronuclear case. There we saturated. Now we'll invert it. The 10 spins which I assumed to be here, I took it there. The 2 spins which were there, I brought it here. That's all I did. How do we do? By applying a pi pulse. We know that when you apply a pi pulse, the magnetization which was here will come back to the from z axis to minus z axis. It just gets inverted. As a consequence, the spin population gets inverted. That's all. Now recalculate the intensities. Very interesting thing happens. Now intensity ratio turns out that before inversion it was 2:2:8:8, 2:2 for carbon and 8:8 for proton. Now after selective inversion of one of the proton, it became minus 6 plus 10 minus 8 minus 8. What is change? See, carbon signal which was 2:2 became 1 is minus 6 and plus 10. That's an enormous change in the intensity. Of course, there is one is negative phase. Don't worry, we will worry about this negative signal later. But there is an enhancement in the signal intensity. That is what is important. Look at it. All we did is inverted one of the proton signals, one of the proton peaks of the coupled doublet. Then we see in the carbon-13, there's a drastic change in the signal intensity. Oh, this is nearly 3 to 5 times enhancement is there. 2 becomes 6 and 2 become 10 here with opposite phase. Okay, so intensities have become 3 and 5. Gain is much more. It is approximately 4 times gain is there. It depends upon the gamma of the proton. Gain is depending upon the gamma. Carbon-13 signal is proton coupled. here. You see, as a consequence, the doublet component we saw has opposite phase. But this is not the what. That's not what we want. Remember, if we in the previous example when we did the APT and other things, we were understanding what happens if I take this Spinnaker sequence like this. We understood what a vector diagram. When you have antiphase components of the multiplet, immediately after that you start decoupling. The vector addition of the opposite signal is such that the gain is nullified. That's what we observed. You don't get the gain. Then whatever we have gained is lost. But that is not our aim. Our aim is to maintain the gain. At the same time, we wanted to do decoupling also. Otherwise, spectrum becomes complex. Our aim was to get a decoupled carbon-13 spectrum. At the same time, see that gain is retained. So what we are going to do for that? This is what it is. See, if we need to do the decoupling, we are going to get doublets. But what happens if I start doing the decoupling here? Look, these are the signal. Just after 90-degree carbon-30 there is no delay. This is what we observed. There is -3 and +5 as the two components of the carbon-13 doublet, which are opposite in phase, anti-phase character, -3 +5. Now, I do the decoupling. There is my receiver is here. Detector is here. I am sitting here and watching. They add up. Opposite vectors in the opposite direction add up in such a way the difference is only retained. Gain is totally lost. That's not what we want. Of course, how do you overcome this? I said we can give a delay. When you give a delay like this, what is going to happen is, we understood by the energy level diagram previously, the minus and plus component, if you give some delay, they will start moving in the other direction. After some time, they will come and overlap here. In the sense, they come in the same phase, in the x-axis. This is where my detector is there. And now, if I do the decoupling, they are not going to get nullified, they get added up. Okay, so this is what we observe. We are going to get the gain in the intensity just by putting a delay there, and the antiphase component we convert it to in-phase components. You understood now. There are two ways of doing a polarization transfer. Selective population transfer, selective saturation. By saturating one of the signal, we transfer this population. That is SPT, selective population transfer. Other is selective population invert. We can invert one of the signal and see how the signal is transferred. And SPI is very good because we got maximum signal intensity. When these 5 plus 3 added up, it is 8. So earlier intensity was 4. I'm sorry, 2 to 4, 8, 8. So 4 times gain in the intensity we have got. Why 4 times gain? Gamma of proton to gamma of carbon is 4 times. So we get almost 4 times gain in the signal intensity here. So now we use this for understanding inept. What is an inept? Inept sequence is like this. It is a sequence for doing polarization transfer. And we are taking the example of the carbon proton coupled spin system. How the polarization transfer is going to help us in not only in gaining the intensity but doing the spectral editing. You can incorporate that sequence in most of the 2-dimensional, 3-dimensional experiment. This inept sequence is always utilized. Let us understand how the magnetization behaves in different parts of the spectrum, pulse sequence here. Let us start with A. In the case of at the point A, what is happening to proton magnetization? Remember, proton is coupled to carbon, so it is a doublet. There are 2 alpha and beta components here. Okay, so both alpha and beta components are aligned along z axis. They are in thermal equilibrium. There is no difference at all. Just thermal equilibrium, magnetization split into doublet because of carbon 13. 2 components, alpha beta. Apply 90-degree pulse. After this is the situation at A. Here, this one. Okay. Now apply 90-degree pulse. Bring the magnetization vector to y-axis. I have done that. Now flip the magnetization to y-axis by applying a 90-degree X pulse. That is position B at the point. This is what happened at the point B immediately after 90-degree pulse. Now what I will do is I will start waiting. I don't do anything. I simply keep quiet. Then what happened? At the point C, there is a delay between B to C. This is the point C. There is a delay between B to C. These alpha beta components of proton start dephasing. One moves like this, other moves like this, depending upon their Larmor frequencies. Because when they doublet, one is at higher frequency, other is lower frequency from the center of the chemical shift position. We know that. Okay, so that's what happens. As a consequence, they start rotating. Let us say after a time delay tau d, they have rotated by 1/4 times JCH. Now at time d, that is just after time c, what we have done is we have applied two 180 pulses simultaneously on proton and also on carbon. Let us see what happens to the proton components. We are going to apply a 180 pulse along X. See, this is Y, this is X. Now magnetization is moving here and here in the Y axis. Now in the X axis, I rotate like this by 180. What happens? This component is here, this component. One which was here came here, the one which was here came here. But they continue to precess in the same direction. You understand what is happening to the proton spin vectors, which was brought here, they start dephasing like this and like this. They start dephasing like this. And rotation on the x-axis like this will like a turning the pancake. The vector start, which was here and here, went here and here. Simply gets inverted. So now beta component is here, alpha is here. They continue to move in the same direction. That is what is happening as far as the proton vectors are concerned. So now at the same time we apply pi pulse on carbon 13. What is happening to pi pulse on carbon 13? Now we have not chosen any particular resonance, right? One particular peak. So we are applying pi pulse. I don't know which phase you are going to apply. It does not matter. What will happen? You are inverting the magnetization. So that means these two and these two spin population should get inverted. That means carbon 13, which still was along z-axis, we have not touched it till now. Remember, you are only talking about proton doublet component. Carbon doublet are still here. Now because of the 180 pulse, from plus z direction, they came to minus z direction. It as good as telling population of the spin states were reversed. Okay, they got inverted. Now N1 and N2 population and N3 and N4 population get reversed. Essentially, it means we are labeling the spin states of alpha and B. Whatever was there, it is changed now. Alpha and beta spin states labeling get changed. So the spin component continue to move. What did we do? By interchanging carbon 13, now we interchange the labelings of spin states of proton. So that is started moving in the opposite direction. I remember before that they were coming here. Because you are applying a 180 pulse, you interchange the spin population. They are coupled to spins, they are coupled to protons. This doublet component of carbon is because of protons, and proton doublet is because of carbon. Now you are inverting this. Means you change the labels of spin states of alpha and beta of proton. That's what happens. Now the spin component continues to move now in the opposite direction. What does it mean? Alpha and beta spin component varied means fast and slow moving components you interchanged. So instead of going in the direction like this, they start moving in the opposite direction. The fast component becomes slow component becomes faster now. Okay. Now let them continue to evaluate like that for some time. After some time, you see that again another 4 by J, if you allow it to evolve, which was here and here, they come exactly opposite. In the sense, Alpha component is along this axis and beta component is like this axis. Exactly opposite antiphase character. Understand? The vectors are in opposite direction. This is antiphase character now. This is at the point E. After time domain delay, when 180 pulses were applied on both proton and carbon. Now at this point, we do another take. Immediately when they are at this position, antiphase position, we do two things. We apply a pi by 2 pulse on proton here, pi by 2 pulse on proton. What is going to happen now? They start rotating the alpha component. Those magnetizations which was the XY component rotates the alpha component to Z axis and beta component to minus Z axis. Remember what is going to happen here. Alpha component which was here along this axis, as soon as you apply 90 pulse on X axis, you can work out by a right hand thumb rule, it goes to the plus Z axis. This component goes to minus Z axis. They start rotating like that. Now finally carbon 13 pulse you are going to apply, which creates antiphase magnetization which is detectable. Carbon 13 pulse is applied, 90-degree pulse, so it creates antiphase magnetization. You are detecting the signal. Now what is going to happen? The signal components of carbon 13 tablets are antiphase. The intensity is -3 and -5. Remember here. Okay, this is moved like this. Carbon 13 finally brings it to this axis, carbon 13 90 pulse, and as a consequence, the carbon 13 signal which has acquired antiphase character, this is the -3 and this +5 is here on this axis. This is where my detector, it is detectable. It is a detectable magnetization. Okay, so what does it mean? You cannot do the decoupling. Remember I said earlier, if you have antiphase components and you start doing the decoupling, because antiphase component vector addition is the opposite direction, whatever the gain you got is lost. We will overcome this later. But you should also remember there is one important point there. In this sense, in addition to this type of polarization transfer, there is also natural abundance carbon 13 signal which is there. When you are detecting carbon, not only you are detecting the gain here because of polarization transfer, there is also natural abundance carbon signal. We have to suppress that. So how do you suppress that? We can carry out two experiments on this for suppression. One, you do an experiment with 90-degree Y pulse. What happens? Then alpha and beta components are +5 and -3 in the intensity ratio. Understand? The carbon signal, carbon doublet component of the carbon, one is 5, another is -3. I have assumed that I have applied pulse on Y axis, 90-degree Y pulse. On the other hand, I can also do another experiment with 90-degree -Y pulse here, the last one, last sequence here. Last pulse, what I am applying, I can apply it I do two experiments. One 90 plus Y, another by -90 -Y. In plus 90 plus Y, this is positive and negative. In the 90 minus Y, the components get interchanged. Now +5 is here and this is negative. Alpha beta components get interchanged. Intensity gets reversed. Now what you are going to do? In both the cases, in addition to this, what are we getting? In this experiment, we get this signal. Okay, natural component it also is there. This is one intensity, this is +5. This adds up as a component because this is all in phase. Natural signal magnetization of carbon is in phase, but they are in antiphase. Now what is going to happen? This will add. Now this and this, if it is present, finally what is going to happen? The transferred magnetization turns out to be 4 and this gets subtracted, it will become -4. Because natural magnetization is adding for that. and it is creating some trouble for us. Okay, so what we will do is, if in fact this is even a worse situation, at this place if you do the decoupling, you will get completely zero signal. Okay, now apply 90 degree minus Y pulse. Now alpha beta components are interchanged. Now this is plus 5, this is minus 3 in intensity. Of course, natural component with in phase is still present. Now if you add, you will get this thing. Again, very interesting thing. There are two experiments we did. In both the cases, we are going to get these things. But what we will do is, we will take the difference of the two experiments, this and this. Now if I take the difference, what will happen? This will get nullified because it is the same phase, same intensity, and this will get added up. And this is what we get. If we take the difference of the two experiments, we get this signal minus 8 intensity and this signal plus 8 intensity. Of course, the antiphase character is still maintained. But now see the gain. 8 intensity. What was the intensity when we started before? It was 2. Compared to proton, 1/4 it is less. But now it is equal to the intensity 4 times gain. Why 4 times gain? It has a relation with gamma, gyromagnetic ratio. You can understand how it is related to gyromagnetic ratio. As a consequence, it became more. Now you look at the intensity pattern for different signals. In the natural, in the conventional carbon-13 NMR, 1D NMR, what is the pattern for CH2? Carbon coupled to 2 equivalent protons is a triplet. No doubt about it. We know that. Whereas in the inept case, we get character signal like this. Why? The reason is the central component of this triplet do not precede at all. It is always along this axis. Only fast moving, slow moving components start moving and start dephasing, moving in the opposite direction. But the one which is at center will not precede at all. It is along the same axis always. So as a consequence, that is not affected. Whereas here this one, this is the gain of intensity by this ratio. This is the gain of intensity by this ratio. I worked out, if you work out, it turns out to be minus 80 plus 8. This is exactly what we saw here. So this is the gain we get for CH2 peak. And what about the CH3 peak? For CH3 peak, it is 1331 intensity in the conventional NM carbon-13 spectrum without INEP. INEP, exactly it behaves like this. Now there is no central component, two components moving in the higher Larmor frequency, two with lower Larmor frequency, they start moving in the opposite direction. As a consequence, it behaves like this. There are two negative peaks and two positive peaks. Again, intensity ratio can be given like this. 3 times gamma over this one, you work out, and it turns out that intensity in the case of CH3 is 12, 12, 12, 12. That's a fantastic thing. Beautiful, right? Now, in the case of the inept case, we can have a coupled inept and decoupled inept. Because this is so far what we observed is coupled inept. Till now, we have not decoupled. Moment you do the decoupling, we know the signal get lost. And this is what happens. You see, you get antiphase components always. This is the antiphase, this antiphase, this antiphase, this antiphase. They are always. Of course, it's a coupled inept. Only thing is, you have to take the center of this as the carbon chemical shift, and of course, you will get two peaks like this. But that's not a great achievement because the signal intensity ratio only when you add up, there is a gain more. So coupled inept is not a most advantageous thing as far as we are concerned. So what we do? We have to do the decoupling. How do you do the decoupling? We have to make sure the antiphase components which were in the opposite direction should come in phase so that they won't get cancelled out. How to do that? This is done by what is called refocused inept. What we do in this case, up to this is known. Now we add an extra block like this. What is this extra block doing? This extra block with this delay 180 pulse on both proton and carbon with another delay, we collect the signal At the same time, switch on the decoupler. This will take care of cancellation of the signal due to antiphase components. How it works? Very simple. Of course, we know we have already worked out in the previous case, in the many examples of APT and others, we have worked out what happens when we give a delay. Just to tell you, at the end of the first delta delay, the doublet component of the CS spin system would acquire a phase like this. Okay, now you give a delay. Delay, how much you give is in my hands. We know how to give. It is 1.3 J is normally accepted value because the J's are different. For example, 1 bond J coupling between CH group is different. Carbons CH2 group, CH carbon coupling is different. If I take CH3 group, CH carbon coupling will be different. They are because of sp, sp2, sp3 carbon couplings. I once pointed out in carbon 13 and NMR, coupling strengths are different. So what to do? How do you adjust the delta? By and large, you have to assume they are nearly equal and take average of this. 1/3 of J is by and large, it is known to be good. It serves your purpose. Put the delay. When you put 1/3 of J, what happens? If it is 1/4, it comes here, 1/2, it comes here. In 1/3 of J, somewhere here, magnetization has moved away. They have acquired a phase difference. Two components, beta and alpha, have moved from here. It started from here, it moved like this. This started from here, it moved like this. And then after some time, you will see they would have acquired some phase difference. Okay. And 180 pulse on the X channel, X nuclei, refocuses the chemical shift. And 180 pulse on the proton inverts the alpha beta spin labels of X vectors. See? This started acquiring the phase, and after some time, the 180 pulse on X nuclei refocus the chemical shift, and the proton, again the labels get interchanged. When the label get interchanged, the last delay, what happened? The spin vectors continue to move in the same direction. After some time, both of them will get aligned along this axis. Now what happens? They are in phase. Do you understand what is happening now? They are in phase. The antiphase component, by applying two pulses and giving two delays, we converted them into in-phase magnetization. Now you can choose the optimum delay which is equal to some value. Now both are in phase. Vector addition enhances the signal. It will not nullify now. As a consequence, we can get a signal with proton decoupling. We can get the carbon with proton decoupling. So what is the length of this J delta? Of course, as I said, average value is 1/3, but you can also do the editing with this. Delta 1/2J gives you only maximum signal for CH. For CH2, delta 1/4J is it gives maximum signal. And for 1/3J, all are equal. More all are equal means all are positive, I would say. All are seen. So we can use this idea for doing editing also. This is called refocused inept. The refocused inept, what we can do is take delta which is equal to 1/4J. All carbons appear as positive. No problems. Put delta is equal to 1/J. Only CH is positive. All others are not seen. Only CH is seen as positive signal. All other become 0. Put delta is equal to 3/4 of J. CH and CH3 are positive and CH2 is negative. You can see that by the intensity plot as a function of delay time. When you see that, look at it. When it is 1/4 of J, all are positive. Exactly at 1/2J. See, CH and CH2, CH2 and CH3 both are negative, 0. Both are 0, it is here. Whereas CH is positive. Positive signal, maximum positive. Now come to 3/4 of J. What is happening? CH3 is negative, CH2 is negative, CH3 and CH are positive. So you can do this identification of carbons based on the proton multiplicities. How? By choosing the delay delta. You can choose appropriate delta and get all positive, or you can get only CH, nullify this, or you get two positive or negative, similar to what you get in other refocusing, other experiment like APT. So what is the advantage here? Look at it. This is a normal NOE spectrum, normal spectrum without NOE, without coupling, without decoupling. This is a carbon 13 spectrum of CHCl3. It is a doublet because I have coupled to single proton. No NOE, no decoupling. Simply acquire the spectrum with a one pulse. You are going to get a doublet. This is JCH and this is the intensity pattern, signal to noise ratio. Same thing, inert spectra, no decoupling, +4, -4 intensity is there. Refocus inert, no decoupling. Only thing is you made anti-phase components as in-phase components. That's all. There is not much change, difference to be discussed about here between this and this. Whereas look at refocused inert with decoupling. Now these two will collapse, add into a single peak. See, enhanced intensity. You get the point. Refocus inert has enhanced intensity. Now we have to compare this with the normal carbon 13 spectrum with decoupling and with NOE. I said in the decoupling, when I was explaining carbon 13 also, I said generally practiced is you acquire carbon 13 spectrum with decoupling and NOE. That is the decoupling experiment of carbon, where we are going to see NOE also. That is the actual signal we get. Now compare that signal with inert. Don't you see there is enhancement in the intensity? This is the advantage of inert. So this is the polarization transfer technique. Just to compare a spectrum like this for a molecule like this, big molecule, nitrogen 15. Of course, I told you this polarization transfer experiment. I took the example of proton and carbon. Does not mean it is applicable only to this. It is a general method I discussed. It can be between any abundant spin to any low abundant spin. Polarization transfer is possible. It can be proton to nitrogen or proton to phosphorus to something else. Anything you can do. You understand? So any low abundant spin you can take, or low gamma nuclei also, and you can do this thing. Okay. And look at it. This is the conventional 59 spectrum. No NOE. This is what you see. It takes ages to acquire. It takes nearly 6 hours to do this thing. Whereas inert experiment gives you enhancement like this. See the advantage of polarization transfer. NMR is basically insensitive technique compared to other spectroscopy technique. But still, we could do something and get the enhancement just playing with the magnetization and spin dynamics. And this is a significant advantage. And if the intensity goes up by 3 to 4 times, your experimental time comes on by a square of that. Instead of doing for experiment for 1 hour, 1 day, we may finish it in less than an hour. It is the biggest advantage, time saving factor. So you see in an example like ruthenium, polarization transfer from phosphorus, this is of course not decoupled antiphase character. This is the conventional spectrum. See the difference in the intensity, lot of enhancement. And this is where you can compare varieties of spectra, different type, carbon 13 decoupling, no decoupling, inert, refocus inert, and all those things. And see the you don't compare just the intensity, you have to compare signal to noise ratio. This noise to signal to ratio is very important. And no doubt, if you can get the refocus inert spectrum and with the broadband decoupling is definitely a better spectrum. So signal intensity maximum enhancement you can see different for different nuclei. Phosphorus 31, if you directly observe with NOE and decoupling with proton, you get 2.24 times enhancement. If you do polarization transfer, you get 2.4. Most important is look at nitrogen 15. Minus 3.4 NOE if you do the normal detection with full NOE from NOE proton and decoupling. Whereas with polarization transfer, it is nearly 10 times gain. See the advantage, 10 times gain in the intensity. Your experimental time enormously comes down. Same thing is true with carbon. So this is the advantage of INEPT. So now as an extension of this, I discussed about depth. You know what is depth? Distortionless enhancement of polarization transfer for spectral editing. The advantage of depth is it distinguishes carbon like APT, which I discussed. At the same time, this is a sensitivity enhancement. Sensitivity enhancement comes because of polarization transfer similar to INEPT. This combines benefits of both the type of experiment. So this is most advantageous. That's why in carbon 13 NMR at the end of the class, I said about depth. I don't want to discuss more again. But remember, most important is the pulse sequence of that is the last flip angle pulse of the 90 degree, or I'm sorry, and the proton channel, not 90 degree, different flip angles. What we can do is normally 3 experiments are done in the depth. This phi is the one which defines the pulse angle. You do 3 experiments, phi, 45, 90 and 135. This is commonly done depth experiment. It is to detect CH, CH2 and CH3 magnetization. So what people have done is, see, this is a comparison of the intensity of different carbons as a function of flip angle theta, flip angle of this last pulse. Okay. When it is done, you see intensity keeps going like this. And this is the place where theta is equal to 45 degree, all the 3 signals are positive. When theta is equal to 90 degree flip angle, these two are practically 0, you get only CH peak. When theta is equal to 135 degree, this is positive, CH is positive, CH3 is positive, CH2 is negative. So, based on the number of protons attached to carbon, whether odd number or even number, similar to what we saw in APT, you can distinguish the carbon by the sign of the signal, whether it is positive or negative. This is what I showed in the graph, how the signal intensity is varying with a different angle. Of course, it depends upon sin theta, whereas earlier I said it depends upon cosine of the theta wave. So this is a simple comparison. This is a normal carbon 13 NMR spectrum. This is a depth 45 where everything is observed. Depth 90, only CH peak is observed. Depth 135, these two are at carbons attached to odd number of protons are positive, CH2 is negative. Okay. And real comparison of the spectrum is like this, and a menthol molecule, this is CH3 only carbons, CH2 only carbons, CH only carbons, and all carbons. How did I get only these? This is what I said. 3 experiments you do. As you said, once you get only CH, once you get all are positive, once you get 2 positive and 1 negative in the 135 experiment. Now there is a multiplication factor for this so that you can scale the intensities equally. Then making addition or subtraction of corresponding 1 or 2 spectra, you can do the editing in such a way from this normal spectrum, you can subtract CH only spectrum, then you get other carbons. Then you can add up CH and CH3 and then scale it, subtract from this, you get only CH only spectrum. Like that, you can play with the scaling factor, do addition and subtraction of this depth spectra of different flip angles. You can manage to get only CH carbon, CH3 carbon, CH2 carbon spectra individually. This is called spectral editing. Most important, very, very advantageous for you for making assignment of the carbons. Now you understood the polarization transfer technique. The biggest advantage is you got the enhancement in the gain. You are able to identify the carbons based on the protons attached to it. At the same time, most important, you are able to get the decoupled spectrum. So biggest advantage. That's why always use depth experiment for your analysis. Okay, so I have told you all about polarization transfer. Not all, I would say, it is only a tip of an iceberg. Lot more things are there for you to understand. Please go back and read your, some more literature, some more books. This is only the concept, fundamentals I have told you. You have to understand. But this idea, what I have given you, should be sufficient for you to start analyzing depth and other things. So we will continue with the next class with a different topic.